Let's get started. We are looking at Z transform properties. We have seen things like linearity, time delay, modulation, and then time reversal and so on. So, we are now going to look at the next one. So, this is differentiation in the Z domain. So, if x of n has Z transform x of z with this ROC, then n times x of n has Z transform minus z times d by dz of x of z, and ROC is same assuming rational x of z, which is the class that we are interested in. The proof is pretty straightforward. So, we have x of z by definition sum over all of n, x of n z to the minus n, and then let us differentiate with respect to z. So, this becomes d by dz of this quantity, and usually when we reach this step, we happily interchange the two operations. Remember that d by dz is a limiting operation. This also is a limiting operation, and you cannot in general interchange these two operations. However, if you had in mathematics some discussion about a series, if the series is absolutely convergent, then in those cases you can do term by term differentiation and term by term integration. So, here because we assume that the Z transform does exist, and because our criterion is absolute convergence, there are no issues taking the d by dz inside. So, this is x of n d by dz, and this of course is minus 1, and then if we multiply by minus z on both sides, so this becomes minus z times and dx by dz, and this is sum over all n, n times x of n z to the minus n, and this is precisely in the form of a Z transform, except that instead of x of n we have n times x of n. Therefore, this has to be the corresponding Z transform. Therefore, we get n x of n having this as the Z transform, and ROC, when you have rational x of z, the ROC does not change. And we will apply this to this particular example. We will start off with our usual a to the n u of n. So, this is 1 by 1 minus a z inverse mod z greater than mod a, and then let us look at minus z times dx by dz of the z transform. So, this is minus z. So, you need to differentiate this. So, this has minus 1 by az inverse power minus 2. So, that becomes this, and then you need to differentiate this, and this becomes minus z power minus 2. All I have done is just simple differentiation. Therefore, this now becomes az inverse by 1 minus az inverse whole squared. So, this of course is mod z greater than mod a, and this has to be the transform of n times x of n. So, you have n a to the n u of n. So, this has transform az inverse by 1 minus az inverse whole squared. We need to get rid of this z inverse. For that, we multiply by z. If you multiply the transform domain by z, you will replace wherever n is there, n by n plus 1. Therefore, this becomes n plus 1 a to the n plus 1 u of n plus 1, and this will be the transform of a by 1 minus az inverse whole squared, and you can cancel 1 power of a on both sides. So, this becomes n plus 1 a to the n u of n plus 1. This has transformed 1 by 1 minus az inverse whole squared mod z greater than mod a, and this in turn is n plus 1 a to the n u of, we will fill that in a minute, this can be written as n plus 1 times a to the n u of n, because yes, very good. So, at n equal to minus 1, this is 0. Therefore, this starts off at n equal to 0, and to reflect that, you have the expression that is usually written in this form. So, as exercises 1 by 1 minus az inverse whole squared, the region of convergence is now mod z less than mod a. So, you need to figure this out, and then 1 by 1 minus az inverse power cap m. Again, two cases here, mod z greater than mod a, mod z less than mod a. For each of these cases, it is important that you derive this, okay. And the way you do this is, you apply the differentiation property to 1 by 1 minus az inverse whole squared. You apply the differentiation property to this transform. One thing that you must have learnt about the transform in the Laplace case, it is a complex function of a complex variable. What is one important property that this Laplace possesses? The same property is true for Z transform. The Laplace transform is an analytic function, which means it satisfies the Cauchy-Riemann equations. Is this familiar to you? If the function is analytic, it will satisfy the Cauchy-Riemann equations, CR equations. Is this? No, it is not been taught, okay. If the function is analytic, in the region of convergence, this is infinitely differentiable. Therefore, you can apply this any number of times. Let us look at the corresponding property for the DTFT. And now what we do is we differentiate with respect to omega, because the independent variable is omega. Therefore, this is d by d omega of x of e to the j omega. Now, how about taking d by d omega inside? Is that okay? Or earlier we did this, right? So, can we repeat what we did earlier? Okay, if the ROC contains the unit circle, then it is absolutely convergent there, and then you can. So, you in DTFT you do assume absolute convergence? So, that is what I am saying. Once you say the DTFT exists, you are saying the sequence is absolutely summable, right? Suppose we have a sequence like x of n equals 1, which is the DC sequence, and later we will see that it has DTFT. So, this is analogous to x of t equals 1 having continuous time Fourier transform 2 pi delta of cap omega. So, clearly x of t is not absolutely integrable in that case, and the sequence x of n equals 1 is not absolutely summable. Therefore, to satisfy the mathematician, we will put a question mark here, and then we will take the derivative inside, but then we will remind ourselves that some conditions have to be satisfied for this to be true. Therefore, this is x of n d by d omega of e to the minus j omega n, and therefore, this becomes minus n times x of n e to the minus j omega n, and hence minus j n, you are right. And therefore, if you take j to the other side, j times d by d omega of x of omega has this as the DTFT, and hence the corresponding DTFT property is this. All right. The only wrinkle here is the interchanging of these two limiting operations, where for the DTFT we do not necessarily assume absolute summability.